Welcome to the course Nuclear and Particle Physics. Course code is BSCP3051. Program name BSc Honors Physics. Today our topic is nuclear binding energy and packing fraction. We will cover the following topics: calculation of nuclear binding energy curve, packing fraction, curve of packing fraction, list of packing fraction and mass defect of few elements, and then references. As a prerequisite or recapitulation, we should have the knowledge of atomic models, concept of mass number, atomic number. Objectives. After studying this unit, we should be able to explain packing fraction, calculate binding energy of a nucleus based on its mass and defect, plot binding energy per nucleon versus mass number, and identify the region of greatest stability and the regions of fission-fusion reactions. Introduction. Mass of an atom is concentrated in the central part called nucleus, which is constituted of neutrons and protons. It has been observed that the mass of a nucleus is always less than the sum of the individual masses of the protons and the neutrons, which constitute it. This difference is a measure of the nuclear binding energy, which holds the nucleus together. This is known as mass defect, represented by delta M. The binding energy of a nucleus is equal to the amount of energy released in forming the nucleus, or the mass defect multiplied by the speed of light squared. A graph of binding energy per nucleon versus atomic number implies that nuclei divided or combined release an enormous amount of energy. The binding energy of a nucleon in a nucleus is analogous to the ionization energy of an electron in an atom. Now we will see how the binding energy will be calculated. We have already discussed the mass defect of a nucleus is the difference between the total mass of a nucleus and the sum of the masses of all its constituent nucleons. Now, MP mass of proton, Mn masses of neutron. So, M total mass of nucleon is ZMP plus NMn, where Z is atomic number equal to number of proton and capital N is the neutron number. Then mass defect delta M will be ZMP plus NMn minus MAZ. The energy equivalent to mass defect is delta E is equal to delta M C square is equal to delta M 931.49 mega electron volt per AMU. We can take one example of oxygen. How its binding energy will be calculated. Its binding energy is 8 MP plus 8 Mn minus mass of nucleon AZ. MP is the mass of proton and Mn is the mass of neutron. Oxygen has 8 protons, so that's why 8 is multiplied. Then mass of proton, it is put up in terms of AMU, and mass of neutron is also put up. So finally we will get 123.23 mega electron volt. Now we will see the binding energy curve versus mass number. Binding energy for all known stable nuclei is positive. Bearing few examples like helium, carbon, oxygen, the values of the binding energy per nucleons vary smoothly. So these points you can see, these are peaks which are observed. Otherwise, they are varying smoothly. There are sharp peaks of helium, barium, carbon, oxygen, indicating that these nuclei are more stable than their neighboring nuclei. For atomic mass, for mass number less than 12, the atoms, the binding energy per nucleon is less. It rises rapidly with increasing A. That is why if we take two light nuclei and fuse them together to form a bigger nucleus, then we will be net gain in the binding energy, which indicates that nuclear fusion is energetically feasible for lighter nuclei. We have seen that fusion reaction occurs for lighter nuclei. So this is because their mass number is less than 12 and they are having less binding energy per nucleon. Now let us go for the cars which has mass number around 50. There is a flat maximum where the binding energy per nucleon is approximately 8.8 mega electron volt. This is the region of greatest stability. So these materials will not show fission and fusion reaction. Now it slowly drops to 8.4 mega electron volt till A is equal to 140. The average binding energy per nucleon between A50 and A is equal to 140, it starts to decrease, and at A is equal to 238, its value decreases to 7.6 mega electron volt. It further reduces as A increases. If we take two lighter nuclei, say binding energy 1.1 mega electron volt per neutron, and fuse them together to form binding energy 7 mega electron volt per neutron. There is a gain in binding energy. This indicates that fusion of lighter nuclei is energetically feasible. If we take heavy nucleus, say around A is equal to 240, and break it into two lighter nuclei, say around 120, A is equal to 120, again there will be net gain in binding energy. That indicates the fission of heavy nuclei, it is feasible. So these are the two reasons why fusion and fission reactions are possible. Next we will discuss about packing fraction. So far we have discussed about mass defect, but it does not convey much information about nuclear stability. It is misleading to say that higher the mass defect, more tightly bound nucleons exist in the nucleus. So another term is introduced by Ashton in 1926. That is packing fraction. Packing fraction is designated by small f, which is equal to atomic mass minus mass number divided by mass number. So that means delta M by A. That is mass defect by A. Now we will see the curve of packing fraction. We will see that F varies systematic manner with mass number A. For very light nuclei and for heavy nuclei, F is positive. Like A less than 20 and A greater than 180. In this case, it is packing fraction is positive. For nuclei with mass number between 20 to 180, F is negative. For very light nuclei, packing fraction is very large. Hence, nucleons in these nuclei are loosely bound. In fact, out of all stable nuclei, nucleons in this place are most loosely bound. As mass number A increases up to A is equal to 16, the packing fraction goes on decreasing till it becomes 0 for A is equal to 16. Now the rest of the part is, as A further increases for A greater than 16 and less than 180, packing fraction is negative. That means these nucleons are strongly bound to the nucleus. There is a flat minima for A greater than 60 and less than 80 at this place. Negative packing fraction also means that in order to break these nuclei into the constituents, we must apply external energy. Beyond A is greater than 180, packing fraction is again positive. So most of the nuclei with A greater than 235 are unstable. Here is a list of packing fraction and mass defect of few elements. So these are listed here for different atoms. It is given first column atom, second column atomic mass, third column mass defect, and fourth column packing fraction. There are some practice questions. First question, define binding energy. Explain stability of nucleus on the basis of this concept. Second is a numerical. Masses of helium nucleus, proton and neutron are given. Find the energy required to knock out nucleons from the helium nucleus. Third question, find the energy required to break carbon-12 into 3 alpha particles. The atomic mass of carbon 12U and mass of alpha particle is 4.0026 Q. Fourth question is also a numerical. The average binding energy per nucleon for alpha particle you have to calculate, given the mass of alpha particle, mass of proton and mass of neutron. Here is some references are given. First book which is consulted, that is Crane. Second, Concept of Nuclear Physics by Cohen. Nuclear and Particle Physics by Mittal. And few slide shares are also consulted.